Okay, in this video we're going to talk about parallel circuits. Now, parallel circuits are ones where there's some sort of a branch in the circuit. So what I mean by that, if I drew this diagram, there's our battery, there's the positive side, there's the negative side. Now, rather than drawing just one single loop, there's going to be a branch in this circuit. So it's like there's three forks in the road. There's three possible directions the current can go. And along each of those roads, there is a resistor. It could be a light globe. It could be a heating element. And those three links now recombine, go back to our battery. So what I want to show you firstly is that there is now a number of different pathways that the current can go. So one possible route of the current could be come out of the battery. So no matter which pathway that they take, they must all pass to this point. But once they get here, there's three different ways they can go. One pathway, some of the current will go through that branch and then will continue back around here to the battery. A second pathway, the current will come around here, but rather than going this way, it could actually go through that branch. The third pathway is the current would come out of the battery and go through this branch and then out that way. So there's three different pathways the circuit can take. Now each of those different pathways is a complete circuit in itself. So this track here, this pathway here, that's one possible pathway, that's one circuit or one loop. There's a second loop this way, and there's a third loop going down through this resistor here and back to the battery. So it's three separate pathways. Now, if these resistors were the same, if those three resistors were the same and they offered the same resistance, then the current would be equally divided into each of these three branches. So, for example, to use a water analogy, if 12 litres of water per second was flowing down this pipe, and this water reached this branch, and it was equally difficult for the water to flow down each of these branches, then a third of the water would go this way, so 4 litres a second would go this way, 4 litres a second would go this way, and 4 litres a second would go this way, and then they would recombine at this point here and would get 12 litres a second coming out back into our tank. So the water would separate like rivers or creeks in a stream, creeks in a river or something, and then recombining. So the total flow going into our branch must equal the flow coming out of the branch. But if the resistors were different, then the currents would be different. For example, if this resistance was really large and this one was a medium one and this was really small, the smaller the resistor, the easier it is for the current to travel through it. So most of the current would travel through this resistor and not very much would travel through this one. And so we need to be able to calculate in this sort of a circuit how much current is traveling through each of those three resistors. So what we're going to do, we're going to call this R1, we'll call this one R2, and we'll call this one R3. Now, the next thing we need to be aware of is that one of the rules of parallel circuits is this. Remember that we said that in any given series circuit, the current everywhere in the circuit must be the same. So in any given series circuit, that's a single circuit, single loop, the current everywhere in that loop must be the same in that single circuit. But this is not a single series circuit. This is a series of parallel circuits. So that does no longer apply, because we've just said here the current at this point here, that will equal the current coming out of the battery, but the current in this branch here will not equal that, because some of the current's going to go through this one resistor and some of the current's going to go through this resistor. So the current going through each of these resistors will actually be different if those resistors are different. Okay, so we're going to go about seeing firstly what the current is through each of those resistors, but one of the golden rules we need to know is that for parallel components, the voltage across them must be the same, and let me show you why. So what I'm really saying here is if that was 20 volts, if that battery there was 20 volts, then the voltage across that resistor there would be 20 volts. The voltage across that resistor would be 20 volts. And the voltage across this resistor, or the potential difference across this resistor, would also be 20 volts. Why? Let's have a look. Let's consider a charge coming out of a battery. Now, at this point, it hasn't gone through any resistor, so each coulomb of charge has 20 joules of energy. Likewise here, 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 and even here. It still hasn't gone through a resistor. Each coulomb still has 20 joules of energy, and it still does. And even when they flow to here and to here, or to here and to here, or to here, 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 and here, they still haven't gone through any resistor. So this coulomb of charge here, this coulomb charge here, and this coulomb of charge here, because none of them have actually spent any energy yet, they will still be at an electrical potential of 20 volts. So each coulomb will still have 20 joules of energy. Now let's look at the other side of the coin. We know that at this side, it must have 0 volts, or each coulomb must have 0 joules of energy before it returns to the battery. Here, here, here. Here it will also be 0 volts, 0 volts, 0 volts, 0 volts, because there's no more resistors for them to pass through. So each of the coulombs of charge, where I'm drawing these blue circles, will all be at 0 volt. So that means that if we look at each resistor, look at the potential difference across them, so we're comparing this one here to this one here, that's going to be 20 volts. The same comparison between here and here will also be 20 volts, likewise here and here. So it's a very important idea. The voltage drop across resistors in parallel will always be equal, or the potential difference across parallel resistors will always be equal to each other. So just to summarize that in a neat little diagram, if I've got 3 resistors, R1, R2, R3, and I could have more in there, I could have R4, R5, I could keep going if I wanted. They're 3 resistors in parallel, then the voltage across them, that's V1, that's V3, that's V2, and that's V1, then V1 will always equal V2, which will always equal V3. And if there's no other components in the circuit, they will also equal the battery voltage. But if there's other stuff happening in the circuit, that won't be true. All right, so let's now look at some other aspects of parallel circuits. So I'll rub this out. Actually, I'll just clear the whole lot, I think. Okay, so now let's do some calculations based on series circuit and parallel circuits. So let's imagine then we've got our parallel circuit. Let's say this circuit, this one, that was R3. Let's say that that is 200 ohms. Here we've got R2, which is 100 ohms. And here we have R1, which is 50 ohms. Oh, another thing that's really important to understand is which way will current always flow. Current will always flow from a region of high potential to low potential. Just like a ball will always fall from a high point to a lower point closer to the Earth's surface. If you had a potential, if you had a really complicated circuit, some sort of really crazy network of wires and resistors, and you had a point there that was at 15 volt potential and a point there that was at, I say a point there that was 12 volt potential, then provided the two parts are linked, current would always flow from the high voltage to the low voltage. Okay, so that's just a very important idea that you'll become more and more familiar with as you go. Okay. Anyway, getting back to our circuit, let's say that this is a 20 volt battery again. There's a positive, there's a negative, the current's flowing this direction, the electrons are flowing in the other direction. So that's the direction of current. Okay, now what we want to do, our goal is to work out the current flowing through each of those resistors. So we could use Ohm's law to work this out. But the problem is, well, actually there's no problem in this case, because we could see that we know that the resistance of this one is 50 ohms, so we know the resistance. Just write down Ohm's law, V equals IR. So we know the resistance, and we know from what we said earlier that the voltage across that resistor will be 20 volts. Okay, so we know that V will be 20, we can work out the current through it. So let's use the local version of Ohm's law to do that. So I'll rearrange this formula. So I equals V over R. Now we're going to work out the current through R1. So through R1, I will equal, now we're using the local version, so the current through the component will equal the voltage across the component, which is 20 volts, divided by the resistance, which is 50. So that is actually 0.4 amps. R2, the current through R2, the second resistor, it will equal, the voltage across it is also 20 volts. So it will be 20 over 100, which will equal 0.2 amps. Now notice, the higher the resistance, the less current's flowing through it. Finally, R3, the current through that resistor will be the current flowing through it, which is, once again, because they're all in parallel, they all have the same voltage across them, so that will be 20 volts. So it's 20 over, in this case, 200, which will equal 0.1 amp. So we now know that 0.4 amps is flowing through that resistor, 0.4 amps. We know that 0.2 amps is flowing through that resistor, and 0.1 amps is flowing through that resistor. Now, all these currents recombine at this point, which means the current now going back into the battery will be those three currents recombined. So that will be 0.4 plus 0.2 plus 0.1. So that will actually equal 0.7 amps. So this is telling us that the current going back into the battery is actually 0.7 amps, which must be the current coming out of the battery as well. So 0.7 amps is feeding this circuit, and then it gets broken up. 0.4 of the amps go this way, 0.2 of the amps go this way, and 0.1 of the amps goes this way. Then they recombine to return to the battery. Okay, now the final thing I want to show you is what if we wanted to work out the total resistance of this circuit? In other words, if I wanted to replace those resistors with one single resistor to have the same effect, what would that be? Now, in the last video, we saw that if the resistors are in series, in other words, in the same circuit, we simply add them together. Well, that is not the case if they're in parallel. To work out the total resistance of resistors in parallel, it's a different formula, and let me now show you what that is. So, resistors in parallel. Okay, the formula, and I'll put this in a different colour, is 1 over the total resistance. We're talking about the total resistance of those three resistors there. 1 over the total resistance is equal to 1 over R1 plus 1 over R2 plus 1 over R3 and so on, depending on how many more resistors you have branched off. So let's do the calculation in this particular example. So if we want to work out the total resistance of this circuit, in other words, how much resistance the current actually feels, it will be 1 over the total resistance will equal 1 over R1. Well, R1 is 50 ohms. So it's 1 over 50 plus 1 over 100. Excuse me. 1 over 100 plus 1 over 200. Okay, so what I'm going to do now, I'm going to make those all the same denominator to make it easier. So that's going to be 4 over 200 plus 2 over 200 plus 1 over 200, which is 7 over 200. So 1 over RT equals 7 over 200. Well, therefore, to work out what RT is, I need to flip that fraction upside down, which means I need to flip that fraction upside down. So RT actually equals 200 divided by 7. And if we work that out, that's actually equal to 28.57, and that's an approximation, 28.57. So I'll just clear that now. So the total resistance is equal to 28.57 ohms. So that means that if I needed to, if I wanted to, I could take all of this away, all of it, and replace it with a single resistor which has a resistance of 28.57 ohms, and that would cause the same current to come out of the battery. Let me prove it to you. So let's now look at this circuit. Let's work out what the current would be if we had a 20-volt battery feeding a single resistor in series, or actually in series with the battery, of 28.57 ohms. Now, because this is an approximation, we won't get an exact answer, but it should be about 0.7 amps. Let's work it out. So we're going to use the global version of Ohm's law now. So V equals IR. We now want to work out the current coming out of the battery, so we're using the global version. So I equals V over R, and because we're using the global version, V is the voltage of the battery, which is 20 volts. R is the total resistance, which is 28.57. So we now go 2820 divided by 28.57. We should get an answer very close to 0.7, and in fact we do. So that's very, very close to 0.7 amps. Okay, so that's the end of our video on parallel circuits. In the next video, we'll look at how we can combine parallel and series circuits together. Thank you.